So now, let us approach one of the most well-known theorems in mathematics here. The idea that the interior angles of a triangle sum to 180 degrees. I'm sure that a lot of you sort of didn't really give this much thought, but this is something here that we know has to, you feel like this is something that you know has to be true here, but they never actually showed you why that's the case, right? It doesn't seem to be the case here. No, it doesn't seem, it just seems to be sort of something that's there. So that given any triangle like this, ABC, and the interior angles 1, 2, and 3 here, no matter what triangle I draw, they have to sum to 180 degrees. So, of course, we could just try to get a protractor and measure all these pieces here. But, again, that doesn't necessarily prove for all triangles. But we may have some ideas with a demonstration like this here. So here's my triangle like so, right? Actually, let me use this here. Here's my triangle like so, ladies and gentlemen. So 180 degrees. Now, we're very familiar with that number because we've seen that number in many places before. In particular, you've seen 180 as two times right angles, or as a straight angle here. So that lends some credence to some information here. So one way that you can try to show that the interior angles of a triangle sum to 180 is to do a little surgery on this triangle here. So, I apologize, this might be a little bit graphic. And we're going to go this here and just do, right? We can kind of take our triangle here, and if this were an actual patient, I basically just ripped their limbs off. Maybe it's a good thing I didn't go to med school. And we can consider something like this here, right? Notice that we can kind of take the triangle here, and we can sort of tear off the corners here, tear off some of the vertices, and put them together, and we see that there's a straight line that's formed along the top here, right? Something like that seems to work. Now, is this a proof? Of course not. This is absolutely not a proof here. But it gives us an idea of what to do, right? Because this gives us some sort of idea that maybe we can use something like this here. We just have to explain it using our postulates and theorems here. Maybe that'll tell us something here. So I'm going to put this to the side. And now we're actually going to try to prove this theorem here. So we need to duplicate the idea of a straight line. Remember that the triangle, we had the angle sort of bunched up around here. We need to duplicate a straight line. Now, considering what we have here, wait a minute. We've done this before. This looks very familiar here, and this is indeed one of the postulates that we talked about here. So what we're going to do is we're going to invoke the parallel postulate here. And we can construct a line like this here. So I can do something like this here. Let me go ahead and construct this here. Let me call this here D. Let me call this here E. So our proof is going to look something like this here. And I'm going to write the proof in blue here. And I'm going to do this as a paragraph. Make this a little easier for all of us here, okay? We're going to construct a line DE through A such that DE is parallel to BC, right? So we can say, so notice how in this situation here, we can actually add things to our diagram. In this case, we're going to be adding what this here is known as an auxiliary line. So an auxiliary line is just a piece of information that we're adding to the picture here. In this case, we needed to draw in a new line for this here. Generally, auxiliary lines are going to be relatively rare, but when they are useful, they are very, very powerful here. So use them sparingly, but they can be very powerful if invoked in the right place here. Okay? So note that in this case here we have this, and we can mention this can be done because of the parallel postulate. So notice that I am justifying this construction by using the parallel postulate here. Now, with parallel lines, oh, that's great. That's wonderful, because now we can move this 2. This 2 gets moved up here because these are alternate interior angles. And this 3 here gets moved up here because they're alternate interior angles as well, right? So that makes sense. So we can say, since alternate interior angles are congruent when parallel lines are cut by transversal, we know angle 2 is congruent to angle DAB and angle 3 is congruent to angle CAE. Note that in this situation here, that looks really good. Now we want to use the fact that these angles sum to 180 here. So in order to do that, I need to convert these to measures here. So by the definition of congruence, the measure of angle 2 equals the measure of angles DAB here. And the measure of angle 3 equals the measure of angle CAE here, right? So we can mention that here. So now we can mention here along this straight line, since these angles lie along a line DAE here, we can say that the measure of angle DAB plus the measure of angle 1 plus the measure of angle 3 is 180 degrees, right? So notice that the goal was to show that the interior angles, these angles 1, 2, and 3 all sum to 180 degrees. Oh, I'm sorry, I forgot about angle 3. I did not mean that here. This should actually be angle CAE here, right? Because that's what this angle is on the straight line. So now we can now do our substitution. I actually substituted a little too early. I apologize about that. So now we have DAB matching with angle 2. We can swap that in here. We have angle 3 matching with CAE here, so I can swap it in here. So now we can say by substitution, we now have the measure of angle 2 plus the measure of angle 1 plus the measure of angle 3 is 180 degrees. And notice that this is always true here. We've actually proved this to be true in Euclidean geometry here.